Morning students. Today we are going to start a very important theorem that is known as Lagrange's theorem. What is its statement? Its statement is this theorem is only for finite groups. So its statement is this: the order of each subgroup of a finite group is the divisor of the order of the group. That means if G is a finite group, let it be of order n, and H be a subgroup of G, then order of H will divide order of G. This is the theorem. Now we have to prove this result. For the proof, let order of G be n, because it is a finite group, so its order will be finite. Let H be a subgroup of G. As H is a subgroup of G, if order of G is finite, order of H is also finite. So order of H is equal to m. Say we let order of H as m. Now what we will do, we will write the elements of H, because H has m elements. So let these elements be H1, H2, Hm, because order is m, order of H is m. So these are the m elements of H, where Hi's are distinct. All the elements are distinct, means different. So now consider one element A of G. Then write coset of H in G is HA. And what are the elements of HA? Right coset is formed by multiplying the elements of capital H with A. So it will be H1A, H2A. These are the elements of H. We multiply all the element by A on the right side, and so on. It will be HMA. So if these elements are distinct, these elements are also distinct, right? So if these elements are M, this is also the coset with M elements. So we write, which implies HA has M distinct elements. Why? Why this? Because if two of the elements of this coset are equal, like this, if they are equal, then by right cancellation what we will get? HI is equal to HJ, but HI's are all distinct, all different, so it will be a contradiction in that case if we take two elements of this coset equal. So finally what we have, that order of HA is also m as the order of the H. Order of H is m and order of HA is also m. Now one thing that we have know from the properties of cosets, that any two right cosets are different or identical. Either they are disjoint or they are identical. So from property Property 3 states that any two right cosets of H in G are distinct or identical. So as we have taken one element A and make a coset HA, similarly we can have more element from G, so we can have different cosets. All the cosets that are distinct, we have to take them. So as G is finite, so how many cosets, right cosets will be possible? Let G be the set of element A1, A2 and so on, AN, because G has n element, we have taken the order of G as n. So let these be the elements of G. H is a subgroup of it. Then we write HA1, HA2 and so on, HAN. These are the cosets which will be either identical or disjoint. Out of these, the disjoint cosets we have to take, which are distinct, which are different from the other. So as G is finite group, so therefore the number of distinct cosets is also finite. As you have seen, if we make the cosets from the elements of G, as the elements of G are finite, the cosets will be finite and we will have to take the distinct coset out of these. So they will be finite, say equal to K. Let the total number of distinct cosets out of this. ਇਹਦੇ ਚ ਕੀ ਕਰਨਾ, ਆਪਾਂ ਜਿਹੜੇ ਸੇਮ ਹੋਣਗੇ ਉਹਨਾਂ ਨੂੰ ਛੱਡ ਦੇਣਾ, ਜਿਹੜੇ ਡਿਫਰੈਂਟ ਆਂਦੇ ਸਿਰਫ ਉਹਨਾਂ ਨੂੰ ਪਿਕ ਕਰਨਾ ਤੇ ਉਹ ਨੰਬਰ ਆਪਾਂ ਮੰਨ ਲੈਣੇ ਆ ਕਿ K ਹੈ, ਠੀਕ ਹੈ. So different K. Then we have the property number 4, which says that G is union of its right cosets, right as well as left. We have taken in this theorem only right cosets, so G is union of its right cosets. So what are the right cosets? These are the, so G will be equal to HA1 union HA2 union HA3. And how many right cosets, different right cosets we have? K. So it will be A1 A2 A3 AK. These will be the different cosets, right cosets, whose union is equal to G. Now if G is union of this, then number of elements in G equal to number of elements in HA1, element in this, plus number of elements in HA2, plus and so on, number of elements of HAK. Because all these are different, they have no element in common, they are disjoint cosets. So the total number of element in G will be equal to the elements in each of these when added. So we add these elements, and number of element in G, we know that the order of G, right? And here the number of element in HA1 is order of HA1, then order of HA2 and so on, order of HAK, right? So order of G will be this. Order of G is n. And what is the order of each right coset? Because each right coset have same number of element, and we have seen in the starting part that HA1, any right cosets of H in G have m elements, as the order of H is m. So there are only m element in each of right cosets. So whether it is HA1 or HA2 or HAK, each will have only m elements. So it will be m how many times? It will be k times. So n is equal to m into k. So what does it show? That n is a multiple of m. and if n is a multiple of m means m divides n, and m is order of h, so order of h divides order of g. So this was the theorem which is known as Lagrange's theorem. So converse does not hold. What will be the converse? As we have seen, the Lagrange's theorem states that order of subgroup divides the order of a finite group. So the converse will be like this: if G is a finite group and M is the divisor of order of G, then there exists some subgroup of order M. So this does not hold. Is not true. Lagrange's theorem is not, the converse of Lagrange's theorem is not true. For this, actually we will take these examples in the later stage, but here you can mention that the alternating group A4 of order 12 has 6 as its divisor, but there is no subgroup of A4 of order 6. So the group A4 whose order is 12 has divisor 6, but there is no subgroup of order 6. So converse does not hold. Now one more important thing that we have seen here, that number of right cosets of H in G. How many? In the Lagrange's theorem, we have seen that the order of group G, that is n, can be written as m into k. This is the order of G, this is order of the subgroup, and this is the number of cosets of H in G. We have taken k as the number of different right cosets of H in G. So from here what we get, if we need to find number of right cosets, how many it will be? Number of right cosets of H in G will be order of G divided by order of H. We will take this on the other side, which is n upon m. So this is known as G double dot H, and its name is index. Index of H in G, or simply you can name it as index. So what is this? Index means number of right cosets. So how many right cosets are there? We have seen they are k in the theorem, and k is equal to n upon m. You can find k from here, which will be n upon m, or you can say order of G divided by order of H. So ਜਦੋਂ ਆਪਾਂ ਗਰੁੱਪ ਦੇ ਆਰਡਰ ਨੂੰ ਸਬ ਗਰੁੱਪ ਦੇ ਆਰਡਰ ਨਾਲ ਡਿਵਾਈਡ ਕਰ ਦਿੰਨੇ ਆ, ਡਿਵਾਈਜ਼ਰ ਤਾਂ ਹੋਏਗਾ ਹੀ। ਲੈਗਰੈਂਜਸ ਥਿਓਰਮ ਇਹ ਸਟੇਟ ਕਰਦੀ ਹੈ ਕਿ ਗਰੁੱਪ ਦੇ ਆਰਡਰ ਨੂੰ ਸਬ ਗਰੁੱਪ ਦਾ ਆਰਡਰ ਹਮੇਸ਼ਾ ਡਿਵਾਈਡ ਕਰਦਾ, ਤਾਂ ਡਿਵਾਈਡ ਕਰਕੇ ਜੋ ਕੋਸ਼ੈਂਟ ਆਏਗਾ ਉਹ ਕੀ ਹੋਏਗਾ? ਨੰਬਰ ਆਫ right cosets of H in G. So in this way we can find the right cosets, total number of right cosets in G. And one more thing, we know that there is a 1-1 correspondence between right and left cosets of H in G. So that is a property of cosets. So if the number of right cosets are k, then the number of left coset will also be k, because दोनों सेम रहते हैं. राइट कोसेट जिन्ने होंगे उन्ने लेफ्ट कोसेट्स होंगे. सो अगर k है राइट कोसेट तो लेफ्ट कोसेट्स भी k होंगे. So this is called index.